This is a presentation by Amelda Sesay
and Achukwu. The aim of the experiment was to study the disorders pancreatic alpha cell hyperplasia and hyperglucagonemia at a genetic and molecular level and find the cause in a subject who does not suffer from glucagonoma.
Glucagonoma is a rare tumor of the alpha cells of the pancreas that results in up to 1,000-fold overproduction of the hormone glucagon.
Glucagonoma is the main cause of hyperglucagonemia and alpha cell hyperplasia.
Hyperglucagonemia is when glucagon levels in the blood are abnormally high.
Alpha cell hyperplasia is an abnormal increase in alpha cells. Naturally, we can conclude that there must be a defect in the glucagon receptors, GCGR.
A pilot study was carried out using mice.
The mice with GCGR's deficiency caused by a homozygous null mutation exhibited the same clinical features as the patient.
Based on this information, researchers hypothesized that the patient most likely suffers from inactivating mutations in GCGR, which causes the clinical syndrome.
Firstly, what is glucagon? It is defined as a counter-regulatory hormone that opposes insulin by promoting glucose mobilization in the liver through glycogenolysis and gluconeogenesis.
Glucagon is released from alpha cells of the islets of Langerhans in the pancreas when blood glucose level is low. Glucagon binds to GCGR. It stimulates a G protein that activates the production of CAMP, a second messenger. This production of CAMP stimulates
glycogenolysis, which is the breakdown of glycogen into glucose when the concentration of glucose in the blood falls below normal levels,
and gluconeogenesis, which encourages the formation of glucose from molecules that are not carbohydrates, such as amino acids, resulting in an increase in blood glucose level.
A 65-year-old female, her brother, and 28 unrelated individuals were used in this study. The diagram shows that her parents are carriers but show no symptoms. Therefore, the patient likely has inherited the homozygous mutation from each of her parents, and the inheritance of the disease probably is autosomal recessive. This diagram portrays a missense mutation where a single nucleotide is changed, resulting in a codon that codes for a different amino acid. Hence, the change from proline to serine due to a homozygous C to T mutation in exon 4 of the GCGR gene.
DNA sequencing. PCR stands for polymerase chain reaction and is used to produce many copies of a specific sequence. The method is as follows.
Temperature is raised to 95 degrees to unwind the DNA helix.
The temperature is then decreased to 50 degrees. Two primers can now bind to the target sequence in the DNA sample. The temperature is increased to 72 degrees. DNA polymerase can start building up complementary strands using the nucleotides. The cycle is repeated until you end up with millions of copies of only your specific sequence.
Plasmid construction and mutagenesis using HEK293 for transfection. The plasmid was created for both the normal GCGR and mutant GCGR. The normal and mutant GCGR genes were subcloned into the PEGFPN3 vector.
Binding assay. HEK293 cells transfected with the normal plasmid or the mutant plasmid were split into 6 well plates. Then, 125I labeled glucagon was added to the wells and incubated with cells at 37 degrees Celsius for 60 minutes.
Camp assay. Cells were then placed in 24 well plates with a culture medium. They were treated with various concentrations of glucagon and incubated at 37 degrees Celsius for 60 minutes. The plates were frozen for 1 hour at minus 80 degrees Celsius, then thawed at room temperature for 3 times.
Immunoblotting. Lysates from HEK293 cells were transfected with the normal or mutant plasmid and were run on STS page.
This binding assay diagram proves that glucagon binds to the normal receptor approximately 10 times more than the mutated receptor. Therefore, the mutated receptor is inactivated as previously hypothesized. This immunoblot shows that the normal receptor and the mutant receptor were predominantly expressed as an 80 kilodalton protein in HEK293 cells, as previously predicted by molecular weights of GCGR and EGFP. This camp diagram portrays that GCGR P86S EGFP has a higher EC50 than GCGR EGFP. Therefore, it has a lower potency.
The researchers concluded that P86S is processed normally and localized in plasma membrane. The P86S mutation lowers the receptor's affinity to glucagon and decreases CAMP production with increasing physiological concentrations of glucagon. Thus, the P86S mutation in GCGR likely causes alpha cells hyperplasia and hyperglucagonemia. Yet, no convincing evidence of glucagonoma syndrome was found, and we now know this was due to the inactivating P86S mutation. This study could establish the basis of further development in characterizing this syndrome.
Thank you for listening.